Hi, this is Professor Smith again, and this video is about wheel encoders. So what are we going to cover in this video? First, we're going to look at what wheel encoders do and why we use them. Second, we're going to go over the wheel encoder hardware configuration. And finally, we're going to discuss software that we use for our wheel encoder. So let's get started with what are wheel encoders and why we use them. As our robot drives around, we're going to want to be able to track its movement. We want to be able to turn left or turn right or drive straight. What wheel encoders do is allow us to monitor the movement of our motors, or actually count the distance that it moves, and therefore either turn left or right based on that count, or straighten up if we started to drift when we're trying to drive straight. The wheel encoders are attached to the motor shafts. As you can see here on this picture, as the motor shaft turns, the wheel encoder actually turns also. And you can also see that there's a small sensor that turns a high or low signal to your Arduino. This high or low signal is what we count, or our software will count, to determine how far our wheels have turned. The wheel encoders we're using this quarter use a magnetic encoder. It uses something called the Hall effect to determine when a magnet has moved underneath the sensor. Our encoders have 4 positive and 4 negative zones on the wheel, so there's actually 8 different states on each rotation of that wheel. Also, the shaft that our wheel encoder is mounted on turns 48 times per wheel rotation. So as the wheel our motor is driving turns once, the wheel encoder wheel will have turned 48 times. So therefore, since we have 8 transitions per wheel encoder disk rotation, so that's just the disk rotation of the wheel encoder, and it rotates 48 times per one wheel rotation, we actually get 384 encoder transitions per single wheel rotation. And this gives us a pretty fine measurement in terms of, as our wheel turns, how far we've actually gone by being able to count 384 times before one full wheel rotation has occurred. So let's talk a little bit about the hardware. Each wheel will have its own wheel encoder. So each one will have the encoder mounted on the shaft, and so in each one will also have the encoder sensor. The wheel encoder requires 3 wires. One is power and the other is ground, so we give it 5 volts in ground. And the third wire is the sensor output. The sensor output returns a high or low signal. Therefore, we can send it to a digital I/O pin, and using that pin in input mode, we can detect if there's a high or low signal on that input, and therefore count the transitions between high and low. So what this slide shows us is how to use the pin that is attached to our encoder. As in use of all digital I/O pins, the first thing we need to do is call the pin mode function. The pin mode function will pass it the encoder pin, in this case it's called left encoder, and we're also going to have to pass it the mode that we're going to use that pin in, and in this case it's going to be input pull-up. Then later on in our code, we can actually read that encoder. So it'll be a digital read and then the encoder pin, and that's going to return high or low. So you should be able to imagine a state machine where when it's high and it transitions to low, you move from one state to another state, and during that transition, you actually count the transition. And then when you're sitting there waiting on the low and then transitions to high, you would once again move back to the original state, and as you're transitioning to that original state, you would count that transition. There's some issues with using our wheel encoder with a straight state machine. Different functions on the Arduino take longer periods of time. For instance, using a serial print is very time consuming and can be very slow. If we're in the middle of doing a serial print and a transition actually was to happen on our encoder, we could miss that transition because the Arduino processor would be doing something else. This is a problem that we need to overcome. The technique we're going to use is called interrupts. Interrupts allow us to monitor the pin while we do other things. The processor that we're using supports 2 interrupts, and we will use 1 interrupt for the left encoder and 1 interrupt for the right encoder. The way the interrupt works is, as the processor is moving along, if it detects a voltage change on our pin, so the pin that we have, let's say, the left encoder attached to, the processor will stop whatever it's doing. So it could be doing a serial print, it could be doing something else. It will then save what it was doing, move immediately to some code for us, which will just count that transition. And then it'll resume whatever it was doing before. Now this happens so fast that our code, the main code that you've been running, won't even notice the fact that it had been suspended for a very brief period of time for us to count that transition. But the nice thing about that is we won't miss a transition because we're doing something else. We'll be able to pick up each transition as they occur because this is done in hardware. The hardware actually detects the transition of the pin, in other words, the voltage change. It then stops what's going on in hardware and then allows us to count it. So what this code here is showing is how we can use our encoder. The first thing we're going to do is create an account. And so right here I have the left encoder account. The only difference here is we need to put the word volatile on it, so it's going to be volatile long left encoder count. We need that word volatile because we're working with an interrupt. The next thing we're going to do is in setup, we're going to set up our interrupt handling. So let's go look up at the encoder setup code. I've moved the encoder setup code to a function of its own, so it's not in setup, but it's actually in a function that we call in setup. This code has a number of things that it does, but the basic thing that you need to understand is it's setting up our encoder to be on pin 2, and it's setting up the pin mode, and then it's attaching the interrupt to that particular pin. You won't need to do this on your own. I will provide you the code for it. The important thing is to realize that it's using pin 2 and it must use pin 2. In other words, you can't change that pin. The encoder, one encoder needs to be on pin 2, and the other encoder actually has to be on pin 3, and that's not optional. The other thing that this shows is the interrupt code. So this is the code that's going to be run when the interrupt occurs. So imagine that you're processing along and you're doing serial prints and other things with your code, and the pin changes, the encoder pin changes from high to low. The hardware will detect that transition, and because of the way we've set up this interrupt, and in fact it's called this attach interrupt command, this code here called left interrupt ISR, which is for interrupt service routine, so the left encoder service routine, will then just count that transition, and immediately your code will be returned to whatever you were doing, so back to that serial print or whatever the code was doing before. As I said, this will happen so fast that you won't even know it, and all you have to do is then later on, if you want to find out how far your wheel is turned, you can access the global variable left encoder count, just like you'd access any other global variable, and it'll tell you how far you have moved. So here's some code. This is my loop code. My loop code does only one thing, which is called output counts, so it's going to call the function output counts. The function output counts is going to count how many times it's called, and that's this count equals count plus 1, and so every time this function's called, it's going to output that. And the second thing it's going to do is every second, it's going to output how far the encoder is turned. And so you can see that there where it's outputting the left encoder count. And this way, what we can do is see how quickly the CPU is going versus how quickly or slowly our count is going up. And we'll find out that the CPU is moving very, very fast. In other words, the processor is moving very, very fast. Even when I turn the encoder wheel at a decent speed, it is still very slow compared to how fast our processor is going. And finally, what you need to take away from this is the fact that the encoder count just changes in increments every single time the wheel is being turned. And in fact, as I said, it'll increment 384 times for every single wheel rotation, and we can access that by accessing the left encoder count variable. As I said in the beginning, what we looked at here in this video were wheel encoders. We use them to count how far we've moved in order to monitor it for things like turns or going straight. We also looked at the wheel encoder hardware, that it needs to use 3 wires. One is positive, one is ground, and the other is the sensor wire, which will hook up to a digital I/O pin. And the third thing we looked at was the software. and the fact that the software we're going to use is going to be an interrupt-driven software, I will provide you with that software, and what you'll need to do is just access the variables left wheel encounter count or right wheel encounter count, and that'll allow you to see how far your robot has moved.